We're given the vector field f and asked to determine if the vector field is conservative. If it is conservative, we want to find a function little f so that the vector field f equals the gradient of little f, meaning f of x comma y would be the potential function. And then if we can find this, we want to use it to evaluate the line integral along the curve C of f dot differential r using the fundamental theorem of line integrals. For a quick review, we know if a vector field is conservative, it will make evaluating a line integral much easier. The test for a conservative vector field in a plane is given here, where if p and q, which are the x and y components of the vector field f, have continuous partial derivatives on an open disk R, then the vector field is conservative if and only if the partial of q with respect to x equals the partial of p with respect to y. So going back to our example, notice how p is equal to 5x plus 7y, and q is equal to 4x plus 5y. So if the vector field is conservative, the partial of q with respect to x must equal the partial of p with respect to y. Well, the partial of q with respect to x is equal to the derivative of 4x plus 5y with respect to x, which would be 4 plus 0, or 4, and the partial of p with respect to y is equal to the derivative of 5x plus 7y with respect to y, which would be 0 plus 7, or 7. So notice in this case, the partial of q with respect to x does not equal the partial of p with respect to y, which means the given vector field is not conservative. So answer here is no, which means there is no function little f, or a potential function, such that the vector field f equals the gradient of f. So we leave this blank, and therefore we're done. We don't have to evaluate this because we can't find the potential function f of x comma y. But this does not mean we cannot evaluate this line integral. Let's go ahead and show how we would evaluate this using this method here, where the line integral along the curve C of f dot differential r is equal to the integral from a to b of f of x of t comma y of t dot r prime of t dt. So we write f as a function of t using the parameterization of the curve given by r of t, and then differential r is equal to r prime of t dt. So the line integral along the curve C of f dot differential r is equal to the integral of f of x of t comma y of t. So notice how here x of t, or x, equals t squared, and y of t, or y, is equal to t to the third. So the x component of f is 5x plus 7y, which is a function of t, would be 5t squared plus 7t cubed, and the y component is 4x plus 5y, which is a function of t, would be 4t squared plus 5t to the third. I'm going to dot this with r prime of t. The derivative of t squared with respect to t would be 2t. The derivative of t cubed with respect to t would be 3t squared. So there's r prime of t, and then we have dt. Limits of integration for t are from 0 to 2. Now let's go ahead and find this dot product. So we have the quantity 5t squared plus 7t to the third times 2t. That's 10t to the third plus 14t to the fourth. And we'd have plus the quantity 4t squared plus 5t to the third times 3t squared. That's going to be 12t to the fourth plus 15t to the fifth. Combining like terms, we have the integral from 0 to 2 of 10t to the third plus 26t to the fourth plus 15t to the fifth. Integrate with respect to t, we're going to have 10 times t to the fourth divided by 4 plus 26 times t to the fifth divided by 5 plus 15 times t to the sixth divided by 6. Simplifying, 5 halves t to the fourth plus 26 fifths times t to the fifth plus 15 sixths also simplifies to 5 halves. So we have 5 halves t to the 6th. So when t is 2, we have 5 halves times 2 to the 4th plus 26 fifths times 2 to the 5th plus 5 halves times 2 to the 6th. And then when t is 0, notice all the terms contain a factor of 0. So we'd have 0 plus 0 plus 0. Simplifying, this comes out to 1,832 divided by 5. Or in decimal form, this would be 366.4. Again, we did not evaluate this line integral using the fundamental theorem of line integrals because the given vector field was not conservative. But just remember, even though it's not conservative, we can still evaluate the line integral using this method here. I hope you found this helpful.